So, hello everyone, how are you all? I hope you all are fine and safe. Well, again, welcome back to Quantum Mathematics. I'm Aman, just welcoming you all to a new amazing video in which we are gonna be proving this amazing identity. We say, since we have talked about an amazing identity in our previous video as well, and that was an integral identity. It was an indefinite integral, so it looked something sort of this. Equals, actually it's the integral of sine of nx times sine of n, actually sine to the n minus 2 of x dx is being generalized as sine of n minus 1x times sine to the n minus 1 of x over n minus 1 plus c. So in our previous video, we have successfully proved that down, right? And as I told you in that video as well, that this identity was in the book that we were following, or that's just going on, the playlist that's just going on here. It was Advanced Calculus Explored, right? So basically this identity appeared in that book, and that's why actually I have promised you guys that I'm just gonna bring a proof video of that, and that way I've done that video, right? And now I'm having this amazing identity. This looks even more crazier than that one, yeah, but it's all right. First of all, I would say that this problem, oh, I'm so sorry, it's not a problem, it's love, right? It's not a problem at all. Okay, yeah, and please, those who call mathematics a problem or questions a problem, I don't like those people actually. It's my personal opinion, it's my personal point of view actually, because it's not a problem though. It's not the thing that you are gonna suffer, right? And if you are suffering it, then you're not actually learning or like enjoying it, right? So that's fine. But it's all right, even though I'm not a mathematician, so I also kind of suffer often in mathematics, but it's all right. I don't suffer, I enjoy that suffering, right? Okay, so let's just get back to this. And yeah, this identity have been also appeared in our book that we were following. So I promised you guys that I'm just gonna bring the proof video of this one as well. So I'm here with this, and this is, believe me, this is gonna take time, and you have to be patient with that, because literally I'm gonna use a tool here, and that's the most important tool, and I think I should write the tool as well. So the tool that we are gonna use for this proof, to prove this down is this identity. Arctangent of theta equals 1 over 2i natural logarithm of 1 plus I theta over 1 minus I theta. Right. I hope you guys have encountered this identity earlier, because this is it's kind of popular, right? It's popular. Okay, but it's all right. I'm not gonna tell you to just watch a proof video of that separately, but I'm just gonna prove this down as well in this video. So basically, firstly we will be talking about the proof of this tool, and then we will be using this tool to just prove this down. And that's why it's gonna be literally lengthy. It's gonna be literally long. So I think without wasting our time, we should just jump right back into the video. Okay, so we have the tool to prove down. First of all, we'll take care about the tool. Okay, so basically we have the tool as its arctangent of theta equals 1 over 2i times natural logarithm of 1 plus I theta over 1 minus I theta, right? Okay. And now here comes the proof. Let your arctangent of theta is z, right? So from here we can say theta is your tangent of z, right? So just note these things down. And why I'm assuming that, because we are gonna introduce the relations between cosine and sine, like with exponentials. So basically, we have sine of, let's say, instead of z, I think I said, yeah, z only. So sine of z can also be written as e to the iz minus e to the minus iz over 2i. And we have for cosine of z, it's e to the iz plus e to the minus iz over 2. And now, some of you, like most of you, might have encountered these two things. But if you haven't seen this anymore, then believe me, it's quite easy to prove down. But you just need to know this thing, Euler's formula, right? So using the Euler's formula, you can just reach these two things up as well. So basically, Euler's formula is e to the iz equals cosine of z plus I sine of z, right? So yeah, what you have to do is you just have to replace your z with minus z, and you will be having two different equations, and from those two equations you can just look for either sine of z or cosine of z in terms of exponentials. Oh, should I prove that down by next time? I think. Oh, let's just do this now. So basically, if we replace z with minus z, so it's e to the minus iz equals cosine of minus z plus I times sine of minus z. And we know that cosine of minus z is just cosine of z, but sine of minus z is minus sine of z, right? So basically, we have the first equation, and the second equation, I'm just copying this down, e to the iz equals cosine of z plus I times sine of z. And just take a look at these two equations. If we just add them up, so basically we would be having e to the iz plus e to the minus iz equals this, and this would be cancelled out because they are in the alternative signs, and we will be having double of cosine of z. And from here, isolating cosine of z would give us e to the iz plus e to the minus iz over 2. And with the same way, you just have to subtract these subtract this equation from this one. So you're gonna have for sine as this thing, right? So it's kind of pretty easy to just prove down. And if we talk about this one, so I have proved this a couple of times earlier in my previous videos, even though I'm having a playlist as well, so you can consider watching that. Okay, so now let's just get back to here. So using these things. So now I'm just going to take the reciprocal. Actually, I'm just going to take the ratio of sine of z and cosine of z. So that's going to be let's just putting down the values. The identity is actually this one over this thing. So basically, we are having e to the iz. Wait a second. E to the iz minus e to the minus iz over 2I times 2 over e to the iz plus e to the minus iz. And we are successfully getting rid of these 2 0, and we are having a factor of 1 over I, and we have e to the iz minus e to the minus iz over e to the iz plus e to the minus iz. So far we have that much thing. And now what we're gonna do here is, you know what sine of z over cosine of z is? It's just tangent of z. So basically tangent of z is coming out to be 1 over I times e to the e to the iz minus e to the minus iz over e to the iz plus e to the minus iz. Right. And guess what? From our assumption that we have here, that we have done here, your theta is tangent of z. So theta is 1 over I e to the iz minus e to the minus iz over e to the iz. I think my z is kind of being depressed. Okay, I'm sorry. Okay. And from here we can just multiply both sides with I. So we have I theta equals e to the iz minus e to the minus iz over e to the iz plus e to the minus iz. Right. And next what we have to do here is we have to let x equals e to the iz. Right. Oh, don't get confused. You just have to follow step by step. Actually, not follow, but to learn actually. I'm just going step by step as much as I can. And here we can say e to the minus iz is your reciprocal of x. That's 1 over x. Right. So basically, we have this thing as I theta equals x minus 1 over x plus 1 over x. And that can further written as x squared minus 1 over x squared plus 1. Right. And I'm just going to multiply both sides with x squared plus 1. So it's going to be I theta times x squared plus 1 equals x squared minus 1. And I'm just going to expand it. So it's I theta x squared plus I theta equals x squared minus 1. And now what I'm going to do here is I'm just going to add both sides with 1 to get rid of this one here, and I'm just going to subtract with I theta x squared both sides to get rid of this term here. So basically we are having 1 plus I theta equals x squared minus I theta x squared. Right. And our next step is going to be isolating. Remember that our arctangent of arctangent of theta was z. So just looking at this equation, we have your so it's 1 plus I theta equals x squared 1 minus I theta, and now just dividing both sides with 1 minus I theta, we're giving us x squared as 1 plus I theta over 1 minus I theta. And from this very equation, we can just square both sides. So that's going to be giving us x squared equals e to the 2iz. So basically, it's e to the 2iz, and we have 1 plus I theta over 1 minus I theta. And now just taking natural logarithm both sides. So that's going to be giving us 2iz equals natural logarithm of 1 plus I theta over 1 minus I theta. Right? And now dividing both sides with 2i, so the isolating z here is 1 over 2i, natural logarithm of 1 plus I theta over 1 minus I theta. And guess what? Your z was arctangent of theta. So I hope you have noticed that down from our previous stuff that we have written over here. So basically from here we can say arctangent of theta is 1 over 2i, natural logarithm of 1 plus I theta over 1 minus I theta. Hence proved. Oh, not done yet. We have another thing to prove down. Okay, so for this one, we are done. Though we can, I can prove that down in a separate video, but I think let's just do from scratch instead of just requesting to watch my another video. And yeah. Actually, I haven't done that before. That's why I don't want to just tell you that please wait for my upcoming video in which I'll be proving this down. But instead of that, I thought let's just prove that down here in this video. Okay, so now let's just coming back to our main identity which we are here to prove down. Just wait a second, let me just check if my recording is going on, and I think I have proven that down in 15 minutes around, I'm not sure. Okay, now we have this identity to prove down. Arctangent of x squared over n squared as it was pi over 4 minus arctangent of hyperbolic tangent of pi x over square root of 2 over tangent of pi x square root of 2. Right. Wait a sec. Yeah. Now it looks fabulous. Okay. So basically now using the tool that we have proved here. Okay. Yeah. So the tool was arctangent of theta equals 1 over 2I natural logarithm of 1 plus I theta over 1 minus I theta. And now I'm going to replace theta here with x squared over n squared. So basically we would be having arctangent of x squared over n squared equals 1 over 2I times natural logarithm of 1 plus I x squared over n squared over 1 plus, oh wait, it's 1 minus, yeah, 1 minus I x squared over n squared. And yeah, and now what we're gonna do here is we are just gonna take an infinite sum both sides with an infinite variable of n, right? So that's gonna be looking like something sort of this. Wait a second, what about my summation sign? Yeah, that looks even more better. Arctangent of x squared over n squared equals this sum as n goes from 1 to infinity of 1 over 2I natural logarithm of 1 plus I x squared over n squared plus 1 minus I x squared over n squared. Okay, and since this 1 over 2I is a constant, so yeah, and you know what? Sum of natural logarithm of some stuff is natural logarithm of product of that stuff. We know that. We have discussed this in a lot of videos of ours, and like previously we have discussed this a lot. And that's what I'm gonna just do here. Actually, I'm just gonna consider taking infinite product inside the argument of natural logarithm instead of just taking the sum of natural logarithm of that argument, right? I hope you all are getting that. Don't get confused. It's all fine. It's the fundamental fundamental properties of natural logarithm. So I'm just gonna call it S instead of just writing it continuously or just repetitively. I just need to just call this S. So basically S is your sum as n goes from 1 to infinity of arctangent of x squared over n squared, right? Okay, and S, I'm just going to consider writing the RHS over there. So it's 1 over 2I natural logarithm of the infinite product as n goes from 1 to infinity of 1 plus I x squared over n squared 1 minus I x squared over n squared. Right. I hope it's visible to you because my writing is kind of worst. Wait a second. I think it's understood. You can just look at that. Yeah. Okay. And now I'm going to introduce something beastie here. What's that? Oh, wait a second. Beastie means I have proved that multiple times, and I'm just gonna use it over here. It's Euler's infinite product of sine function. Yeah, I have proved that. Not sure, but 3 times. Yeah, I have proved that 3 times. And the one like among those three videos, I took 1 hour in one video, and that was literally from this one. The formula for the double angle of sine. From here to here, wait a second, I haven't written the formula yet. So basically it's your product z times n, the product as n goes from 1 to infinity of 1 minus z squared over n squared pi squared is your sine of z. So this one. And I literally took 1 hour, I think more than that, but still it's wonderful. And I must recommend you to just watch that video. Because surely you're gonna get a lot of things out of it. So basically this is the Euler's infinite product of sine function. And now what I'm gonna do here is I'm just gonna try to evaluate these two products. Basically this can be written as 1 over 2i natural logarithm of this product over this product, and the arguments are 1 plus I x squared over n squared, 1 minus I x squared over n squared. Right. Okay. And now how am I gonna do that? So I'm just gonna consider the numerator product as n to the r, right? So basically that is this product as n goes from 1 to infinity, of 1 plus I x squared over n squared, right? And now just take a look at both of these products here. If I wanted to just convert this product into in something sort of this one, so what I'm gonna do, just take a look at this. We are not having pi squared here, right? Okay, and we are not having I over here, right? So let's just talk about this. So basically what I'm going to do here is I'm just going to consider, because and just take a look at this, that we are having a negative sign here and we are having a positive here. So for that case we have to consider this one. Basically what we have to do is for this, like, you know what, this is a general form, right? And if I want to make the general form to look like this one, what I'm gonna do here, I'm just gonna substitute something in here. So basically minus z squared over pi squared is I x squared. Because rather than these things, everything is perfectly fine placed, right? Yeah. And from here, if I'm just gonna look for z, and that's how I'm just gonna look for the product. Because when I substitute, wait a second, let's just isolate z here. So z squared is gonna be minus I pi squared x squared, and from here just taking the square root both sides, so z is coming out to be pi x square root of minus I. And now guess what, when you substitute this back over here, so you're gonna get this very product, right? So that's amazing, literally amazing. So basically your argument for z in order to get this one is pi x times the square root of minus I. And I need to look for the square root of minus I, right? And let me just explain you. Wait a second. Yeah, everything is fine, I think. Yeah. Wait. What we were having is, oh wait, it was s, right? So s equals 1 over 2 I natural logarithm of the product of 1 plus, what was that? Yeah, it was 1 plus I x squared over n squared over 1 minus I x squared over n squared. Okay, and now let's just talk about this square root of minus I. Using the Euler's formula, so if I replace z with pi over 2 here, basically minus pi over 2, so basically your z is minus pi over 2, so it's e to the I minus I pi over 2, and cosine of minus pi over 2 is just 0, and sine of minus pi over 2 is minus 1. So minus 1 times I, it's minus I, right? And just taking the square root both sides, so that's going to be giving us e to the minus I pi over 4 is the square root of minus I, right? I hope you are clear with that. It's pretty easy to just think about that. It's easy. And if we just try to plug this argument down over here, so basically your e to the minus I pi over 4 is cosine of minus pi over 4 plus I times sine of minus pi over 4, and that's gonna be looking like something sort of this. So basically the square root of minus I is 1 over square root of 2 times 1 minus I, right? Yeah, so that's how we can replace this square root of minus I as pi x over square root of 2 times 1 minus I, right? And for my convenience, I'm just gonna consider this one here. Wait a second, guys, let me just copy down. And yeah, so basically we are having z equals pi x over the square root of 2 1 minus I, and I'm just gonna write it as u minus iu, and our u here is pi x square root of 2 over square root of 2, right? In order to just get rid of some messy things. Yeah, okay. Okay, so yeah, and now, so basically what we are having so far is, for this very product, so yeah, so basically, yeah, the product as n goes from 1 to infinity of 1 plus I x squared over n squared equals sine of, it goes for pi x over square root of 2 1 minus I, which we have considered as u minus iu. Yeah, actually just writing this pi x over square root of 2, it's kind of just like it's kind of confusing. So to get rid of that, I have considered as, I have just made it safe, right? So, and we have yeah, this z, so basically it's pi x over square root of 2 1 minus I, which is sine of u minus iu over u minus iu, right? And guess what, taking the conjugate, actually complex conjugate of this one, though you can go with that method as well, the way we just look for this one, but in order to just save our time, we can just take the complex conjugate. Complex conjugate. So that's going to be looking like something sort of this. Product as n goes from 1 to infinity of 1 minus I. So basically, the sign of I is being replaced with the another, like alternative. If you're having a negative, then it's going to be changing to positive. If you're having the conjugate of that, and if it's in positive, then it's going to be negative. Like if you're taking the conjugate of that. So basically, it's, yeah. On the right hand side, we would be having sine of u plus iu over u plus iu. So that's how we literally just find the values of these two infinite products. And next what? Let's just substitute back over here. So yeah, this is amazing. This is literally amazing. Okay. So let's just substitute them back over here. And let's just talk about furthermore. I'm loving it, damn it. Okay. Yeah. So our S is 1 over 2i natural logarithm of the product. The numerator is sine of u minus iu, and factoring out u here, 1 minus I, sine of u plus iu, u times 1 plus I. And from here we can say that it's your 1 over 2i natural logarithm of, am I going right? Yeah. So it's gonna be 1 plus I over 1 minus I, right? Because we just getting rid of these two, these u's here, and we are having sine of u minus iu over sine of u plus iu. Oh, basically, let me just write that down here. 1 over 2i natural logarithm of 1 plus I over 1 minus I, and it's sine of u minus iu over sine of u plus iu. And yeah, so basically I'm just gonna consider these things as R, basically ratio. That's why. And I'm just gonna replace R with, actually S equals 1 over 2i natural logarithm of R, and R is 1 plus I over 1 minus I, and times we have sine of u minus iu over sine of u plus iu. Yeah. So basically we are just gonna working on R from here onwards. So your R is, oh wait a second, let me just talk about this part. 1 plus I over 1 minus I. And what I'm gonna do here is, I'm just gonna multiply. What we can do here is, it's 1 plus I whole squared. Actually, multiplying and divide with 1 plus I, right? 1 plus I actually. So it's 1 plus I times 1 minus I is just 1 minus I squared. So that's gonna be giving us 2, right? And if we expand this out, so it's 1 squared plus I squared and plus 2i. So basically I squared is minus 1. So 1 minus 1 cancels out, and we will be having 2i over 2, which is just I. So basically this part is going to be just I. So I times sine of u minus iu over sine of u plus iu. Right? Okay. And now let's just talk about this. I think it's 33 minutes, yeah. I think it's gonna be touching 1 hour, I'm not sure. But I'll be just trying to just cover it as soon as possible. But I'm not gonna do this as let's just hurry up. We just have to complete this on as soon as possible. No, it's not like that. Just take a deep breath and let's just dive into it. Let's take time, dude, because we're not just wasting here, we're learning a lot of things, isn't it? Okay. Yeah. So your R is I times sine of u minus iu over u plus iu. And again, you know what? I have proven using this thing, Euler's formula. This is goddamn important, dude. Like literally, in this only video, I have talked about this a lot of times. And you know what? This is literally very important. I have proved the expansion of these twos using the Euler's formula. So I'm just going to use that now. You can consider watching that proof. Okay, and before that, we know that. Oh, wait a second. Yeah, you can see that. So basically, we know that like the relation between hyperbolic sine and sine, like trigonometric sine and hyperbolic sine, and the relation between trigonometric cosine and hyperbolic cosine. So the relation, even I have proved that down as well, and I'm not going to talk about that in this video. So your sine of IU is hyperbolic sine of u, and your cosine of IU is hyperbolic cosine of u. So yeah, that's how we're gonna talk about. In actually, those two are gonna helping us in this expansion. So your R is I times, expanding this down, so it's sine u cosine of IU minus cosine of u sine of IU over, and it's just we just have to use the plus sign in between to get the expansion of the denominator. So just copying that down. Oh, wait a second. Oh, wait. Yeah. Perfect. Plus cosine of u sine of IU. Right, and we have R as, okay, so basically from this very, you can say, yeah, from these two things, we know that sine of IU is I times hyperbolic sine of u, and the cosine of IU is hyperbolic cosine of u. So just let's just replace those things down here. So basically it's sine of u, and this cosine of IU is hyperbolic cosine of u minus, we have cosine of u, and basically I times hyperbolic sine of u. So basically I'm just going to write that I over here, and it's hyperbolic sine of u. And so with the denominator, sine of u hyperbolic cosine of u plus cosine, wait a second, it's I, right? The I cosine of u hyperbolic sine of u. Okay, so we are that much. We are there that much actually. And now let's just go further. Okay. And next, what we're gonna do here is we're just gonna play around some manipulation here, right? Yeah, this is mathematics. Okay. So I'm just gonna divide numerator and denominator with cosine of u hyperbolic cosine of u, actually times. So what R is gonna look like is I times, so it's sine of u hyperbolic cosine of u minus I cosine of u hyperbolic sine of u over cosine of u hyperbolic cosine of u over, we have sine of u hyperbolic cosine of u plus I cosine of u hyperbolic sine of u over, we have cosine of u hyperbolic cosine of u. Okay, and now I'm just gonna split this fraction into two different fractions. So I is sine of u hyperbolic cosine of u over cosine of u hyperbolic cosine of u minus I, it's cosine of u hyperbolic sine of u over cosine of u hyperbolic cosine of u over, we have to do the same for the denominator, for the big denominator actually. sine of u hyperbolic cosine of u over cosine of u hyperbolic cosine of u plus I, and we have cosine of u hyperbolic sine of u over, we have cosine of u and hyperbolic cosine of u. Yeah. And what we're having here, cancellation, a lot of cancellations here. Yeah. And you know what? Hyperbolic sine of u over hyperbolic cosine of u, it's hyperbolic tangent of u. And we know about the trigonometric function as well. It's sine of u over cosine of u, it's just tangent of u. So let's just do these things here as well. Okay. And we have our I, actually r equals I. And we are having sine over cosine tangent of u minus I, hyperbolic sine over hyperbolic cosine, hyperbolic tangent of u, and tangent of u plus I, hyperbolic tangent of u. And I'm just gonna multiply, taking a factor of tangent of u from both the numerator and denominator. That's gonna look like tangent of u over tangent of u, and it's 1 minus I, hyperbolic tangent of u over tangent of u over 1 plus I, hyperbolic tangent of u over tangent of u. So R is gonna look like I times 1 minus I, hyperbolic tangent of u over tangent of u over 1 plus I, and it's hyperbolic tangent of u over tangent of u. Yeah. So far we are having that much amount of thing. I'm just gonna box it off because this is important. And I'm just gonna get rid of this one. And now, you know what? I'm gonna use an amazing identity here that we have proven here in this video only. And that is your arctangent of theta is 1 over 2I natural logarithm of 1 plus I theta, and it's 1 minus I theta. Wait a second, actually what we can do here is we can just talk about oh wait a second, is that what we're gonna do? Because yeah, so it's 2I times arc, just multiplying both sides with 2I, so arctangent of theta is natural logarithm of 1 plus I theta over 1 minus I theta, right? And from here onwards we can just take e raised to these two things, so that's gonna be helping us out as e to the, and we can consider, like before taking that stuff, we can consider taking the reciprocal of the argument of the natural logarithm. So basically taking the reciprocal of that, so it's 2I arctangent of theta as natural logarithm of 1 plus I theta over 1 minus I theta to the negative 1, right? Oh, actually I'm just messing up here because we know that we have a property, a well-known property that says natural logarithm of a plus b is minus of natural logarithm of b over a. Actually it's not a plus b but a over b. So we are having minus of natural logarithm of, I'm just going to write the minus term in the numerator, that is 1 minus I theta over 1 plus I theta, right? And we know that. And from here we can just multiply both sides with negative, so it's minus and it's plus. So basically we are having that much thing. And now what we're going to do is to raise these things of e power. So it's your, we know that e to the natural logarithm of anything is just that thing. So we are having 1 minus I theta over 1 plus I theta as e to the minus 2I arctangent of theta. Right. And for our case, we have theta as the ratio of hyperbolic tangent of u and the tangent of u. Hyperbolic tangent of u over tangent of u. So basically that's gonna be giving us the same stuff that we are having in this part. And we know that I is e to the I pi over 2. Because just imagine, e to the iz is cosine of z plus I sine of z. And when you replace z with pi over 2, then we know that cosine of pi over 2 is just 0 and sine of pi over 2 is 1. So 1 times I is, it's just I. Then e to the I pi over 2, it's I. So yeah, let's just go down, do these things down. So basically our R is gonna be I can also written as e to the I pi over 2, and we have that stuff when we replace theta with hyperbolic tangent of u over tangent of u. So yeah, so that stuff that can also be written as e to the minus 2I arctangent of hyperbolic tangent of u over tangent of u. Right. And from here we can just combine these two e terms. So that's gonna be looking like something sort of this, e to the I pi over 2 minus 2 times arctangent of hyperbolic tangent of u over tangent of u. This is our final step here. Not final, but like to talk about R. I hope my recording is going on perfectly and you can see all the stuffs perfectly as well. And from this, wait a second, actually, oh, yeah, wait a second. Our S was 1 over 2I times the natural logarithm of R. So basically, let's just talk about the natural logarithm of, like taking the natural logarithm of this very equation. So if we talk about natural logarithm of R, so that whole stuff is just the result of this part, because natural logarithm of e is just 1. So this part is gonna be I times pi over 2 minus 2 arctangent of hyperbolic tangent of u over tangent of u. Right. And finally, our last step here is, let's just plug this natural logarithm of R in this result in order to get our final sum, that is this one. And yeah, it was an amazing journey, wasn't it? So finally we have our S as 1 over 2I, and like finally just substituting back here. So it's I times pi over 2 minus 2 times arctangent of hyperbolic tangent of u, u over, it's not this last step, but it's the second last or the third last step. And here we can we just got rid of these two i's here, and we can just multiply this 2 back into this parenthesis. So our S is going to look like pi over 4 minus 2 cancels out, so we would be having arctangent of hyperbolic tangent of u over tangent of u. Guess what? What was our u here? Just take a look at this. Guys, literally we are here. So basically substituting u equals pi x times the square root of 2. That's literally gonna give us our S. Right, so finally S equals this sum as n goes from 1 to infinity of arctangent of x squared over n squared. Oh, wait a second. Is everything fine? Yeah. Actually, you know what? My phone has a disadvantage in it that it gets hot too quickly. So for that, I just need to check that out if whether the recording is going on or not. It's kind of weird, but I'm sorry. I just need to check this out. Okay. So this part is the sum as n goes from 1 to infinity of arctangent of x squared over n squared, and successfully we are substituting this back over here, and finally we have pi over 4 minus arctangent of hyperbolic tangent of pi x over square root of 2 over tangent of pi x over the square root of 2, and hence proof. Guys, that was literally amazing. That was extremely amazing, and I did really loved it. The way we just moved from here and there and just finally reaching up to the final result. So that's how mathematics goes on. Okay, yeah. Guys, another good news is that we have done all the things in 51 minutes, and I'm just gonna talk with you a little bit, not that much. But yeah, I hope guys you just got to learn something out of this video, because we did a lot of things, and even I didn't request you to just this video has a prerequisite that we are gonna use an identity which we have used. Actually, that identity which we proved earlier, and that we have taken 15 minutes to prove down. Though I would have left that as a prerequisite, but I just thought let's just do that in this video only, so that you guys cannot say that Aman did everything out of nowhere. It doesn't mean so. Actually, you know what? That thing should be proven definitely for this identity, because the base of this, the base of the proof of this identity begins from there only. So for that case, I just thought instead of just taking it as a prerequisite, let's just prove that down in this video. And yeah, we successfully did that, and we even did this one as well. I think I never got stuck here, right? But yeah, that was perfectly fine, and I really loved it. I really enjoyed it a lot. As always. So yeah, goodbye guys, take care, love you, and I think I'm just gonna work for the next chapter of the book that we are looking for. That's the Advanced Calculus Explode playlist, but I just need time. Yeah, actually I'm just looking for some other stuff that is I just saw something in that book only, that is Fronali's integral. I think, you know what, I have listened that stuff earlier, but I haven't just thought about that to prove down. But now I think I just need to talk about that once. So surely we'll talk about that. Okay, but not now. Yeah. Okay, so goodbye guys, take care, love you, and just love your life, enjoy your life. Just take a smile on your face, because everything is fine. Yeah. My hands are working, I'm just working here, that's it. And you guys can see, watching, you guys can see working me here. So that's amazing, isn't it? So yeah, and I'm sorry guys if you find it weirdness in my behavior, and I think it's not like that. I'm just being happy. Okay, I'm sorry guys. Okay, goodbye guys, love you, take care, and just get back to the next video, because we are gonna take a lot of stuff like that. Those are beastie stuffs.